Welcome. Education is a privilege, but it can be hard to remember that when the going gets tough. As an undergraduate, I went to a big state school, and since then people have asked me whether I would recommend that school. And I tell them, you can get an excellent education there, but no one will make you. And what I mean is that a person's education is really up to them. We each have to continue to make choices to apply ourselves to the best of our ability. Since that time, I've done scientific research for a long time, and sometimes the going gets hard there too. Then I have to remind myself to have an attitude of gratitude, to realize that I have been given a tremendous opportunity, and that if everything went right the first time, it wouldn't be called research, it would just be called search. So as you get frustrated from time to time, try to take a step back and realize the tremendous opportunity you've been given to learn and apply yourself to the best of your ability. I'm Dr. Courtney. In this problem, we're asked to find the final speed of a runaway toboggan after a load of snow is dumped on it. This is a completely inelastic collision, and the two masses basically combine and operate as a single mass after the collision. We would like to use conservation of momentum to do this, but conservation of momentum is a vector quantity that involves some assumptions for it to be true. First of all, there can be no external forces acting on the system. Now, the snow is falling in the vertical direction due to an external force of gravity. So actually, momentum in the vertical direction is not conserved. However, the problem asks us about the final speed of the toboggan, which is traveling only in the horizontal direction. And so momentum is conserved in that direction because there are no external forces acting on it. So we need to keep this in mind so that this problem essentially becomes a one-dimensional problem only because that's the component that we're interested in, and momentum happens to be conserved in that direction. So the final speed we'll call v sub f. And let's go ahead and note that momentum in the y direction, which will be our vertical direction, is not conserved due to gravity. But the momentum in the x direction is conserved. So as we develop this problem, initially, we have this toboggan that's traveling at an initial speed. We'll call that mass 1, and that's equal to 8.5 kilograms. And so V1 initial is equal to, we're told that it's traveling at 20 kilometers per hour, but that's not MKS units, so if we convert, that's 5.55 meters per second. And then intermediate, along the way here, we have a load of snow that I guess was up on a tree branch that falls down. That snow, we'll call that M2. And we're told that's 14 kilograms of snow. But that V2 initial in the x direction is 0. Because it has only a vertical component of speed, of velocity. So then, in our final situation, we have the toboggan with the load of snow on it. And so its mass is going to be the sum of the masses. So we have M1 plus M2 here, and it has some final speed in the x direction that we don't know. That's what we're being asked to compute. So now let's establish a coordinate system. We're going to say that x is positive to the right, and that y is positive up. And again, we're focusing our attention to what's happening in the x direction only. So as we make a plan for this, in the x direction, we're going to set the initial and final momenta equal to each other. Then we want to express those momenta in terms of masses and velocities, or speeds. So we have mass 1 for the toboggan, mass 2 for the snow, V1 initial for the toboggan, V2 initial for the snow, and V final. And then we want to solve for the quantity of interest, which is the final speed. And then we can go ahead and substitute values to compute a figure for that. So I think we're ready to evaluate this problem. So the initial momentum in the x direction is equal to the final momentum in the x direction. The initial momentum is comprised of the momentum of the runaway toboggan and the momentum of the snow initially. And so we have m1 times the initial speed of the toboggan plus the mass of the snow times the initial speed of the snow in the x direction. And that's going to be equal to the sum of the masses after the inelastic collision times the final speed. Now, the initial speed of the snow in the x direction is 0. And so this term is 0 because that's 0 in the x direction. And we're solving for the final speed. So the final speed will be equal to the mass of the toboggan times its initial speed divided by the sum of the masses. And we can go ahead and substitute values now, and that's equal to 8.5 kilograms times 5.55 meters per second divided by the sum of the masses, 8.5 kilograms for the toboggan and 14 kilograms of snow. So then we can compute that the final speed is equal to 2.0987 meters per second. That's too many significant figures to report in a final answer. So let's consider our given values. We have 2 significant figures there in that mass, in those masses. So let's report our final answer. To 2 significant figures, 2.1 meters per second, or if you want to convert that back, to 7.6 kilometers per hour. Now, how can we tell whether this answer makes sense or not? First of all, we start with unit analysis. And if we check back, when we substituted values here, we have kilograms divided by kilograms, because kilograms plus kilograms is still kilograms. And so that unit cancels, and we're left with units of meters per second, which is what we would expect for a speed. So that checks out. What about the magnitude of our answer? Well, we expect the final speed to be less than the initial speed because we've added more mass to it without adding more, and that mass had no initial component of velocity or speed in the x direction. So should be less. What should be? The final speed should be less than V1 initial, and it is. But how much less? So the initial speed was 5.55 meters per second. Our final speed is 2.1 meters per second. That's less than half. Well, let's consider the masses. It's not speed that's conserved here. It is momentum in this direction. So if we consider that the mass of the snow was greater than the mass of the sled, so since the mass of the snow, which was m2, was more than twice the mass of the sled, we expect the final to be less than half of that the initial speed of the runaway toboggan. And so let's see if that's the case. Our initial speed was indeed less than half, and so that magnitude makes sense as well. So between unit analysis, which was pretty quick in this particular problem, and considering the magnitude relative to the initial magnitude of the speed, we have confidence that this is the correct answer.